we're going to keep going through electronic stuff. Last time we talked about resistors and Ohm's law, and we talked about putting resistors in series. And remember, when you put resistors in series, they each have the same current, because so series, the way to think of that is that if the current goes through one of them, it has to go through the other one. Okay, and so any current that goes through one has to be going through the other one, and so they both have the same current, but they have different voltages. And so putting resistors in series is a way to change the voltage if you need a smaller voltage than is provided by the battery or whatever. So we're going to start by, so back to resistive circuits. Resistive circuits are circuits that just have resistors. And we're going to start out with just kind of like a refresher type thing. So I have 9-volt batteries up here. I guess someone from every table can come get a 9-volt battery. And I want you to set up this circuit so that you have the 9-volt battery going to a 1,000 ohm resistor, and then going to an LED, and then back. So see if you can use the breadboard and the resistor and an LED for this. Okay, remember that the 1,000 ohm resistor, it follows that up there. So a 1,000 would be brown, black, red. Sort of think about it. So this is part A, and we got that to work. And now you're going to have 9-volt battery to a 1,000, to a 1,000, to an LED. And so before you set this up, do you expect the current through that LED to be higher or lower this way? Yeah, so if you think about, so what we're doing here is when we combine these two, it's, these two are in series, right? The current has, any current that goes through one has to go through the other one. And so to lump these two together and think of it as an equivalent resistor, you just add those two. So what we have now is like a battery going through a 2,000 ohm resistor to the LED. Okay, well, Ohm's law says that that if you have twice the resistance and the same voltage, then the current has to be half. So you should hopefully see a dimmer light in the LED if you set this up. Okay, so set up this circuit with your breadboard. Now we're going to do two that are in, it's called parallel, and that's the first thing we're going to talk about today mathematically. So we're going to set it up like this. We have the 9-volt battery. and a 1,000 ohm resistor there, and a 1,000 ohm resistor there. And then it's going to go from those two to the LED and back to the ground. So this is 1,000 ohms. And this is 1,000 ohms. Okay, so this is going to do something that maybe is a little surprising at first glance. What happens in this case is that we're going to see that LED get a little bit brighter than it was when we just had the single resistor. Okay, and the way to make sense out of that is, remember, you can think of resistances as like restrictions in a pipe. Okay, and the current is the amount of fluid flowing through this pipe. Well, in this case, the fluid flowed through the first one and it slowed down the current. And then it had to flow through the second one, which slowed it down more. Okay. In this case, all the fluid has two choices to go. So it can go this way, and that would restrict it a little bit. But in addition to that, it has another option. So it's like all this fluid has two chances to get back to this location, you know? And so you can think of it in a way, in an accurate way, twice as much fluid can go through this as it would if this was gone. Okay, so wire this one up and see if you can see that LED is a little brighter this way. This should be the brightest of all three. For resistors, these are called in parallel. More current gets to the LED. And so the LED is brighter. Okay, so I want to go through, so here's what I'm going to do. I'm going to go through doing the math of circuits when resistors are in parallel like this. And then I'm going to go back and answer any questions anyone has on the homework. And then we'll see where we are with time. But the next thing we're going to talk about is using multimeters to measure voltages and currents. Okay, so the last combination of resistors that we talked about was series resistors. And the way to think about series resistors, so remember, for series resistors, any current that flows through one has to flow through the other one. So must flow through the other. And the result of this is that the current flew through both of them is the same. You know, there are no options. Like all the current, like if one of those resistors backs up the current a lot, it backs up the current through the first one too. Okay, so the current is the same through any elements in series. Okay, so if we look up at this, this B, the current flowing through the first resistor is the same as the current flowing through the second resistor, and it's the same as the current through that LED because they're all in series. There's no other path. If you go through one of these, you have to go through all the other ones. Okay, so now we're going to talk about parallel resistors. And for parallel resistors, the current can choose one path or the other. And the important thing here is that the voltage is the same for any elements in parallel. Um, and so to calculate the current through each of the parallel resistors, if you lump the two parallel resistors together, the rule is that 1 over the equivalent resistance of the two together is equal to 1 over R1 plus 1 over R2. So that's the easiest way to remember it. They're all just reciprocals. Remember when we did that for series resistors, we just added the two resistances. So mathematically, the way this works is now if you solve for R equivalent, you get R1 times R2 divided by R1 plus R2. Okay, so let's see an example. So let's say we have a plus 5 volt electric potential there, and we have a circuit where it goes through a 100 ohm resistor that way, and then a 1000 ohm resistor that way. And then it goes to the ground. This one's 1000. And we want to calculate the current through each resistor. And then, so let's do that. And then let's also calculate the total current drawn from the battery. Okay, so first we have to identify that these are parallel. You know, like the most common way to draw parallel resistors is to have them actually on physically, mathematically parallel pieces. But the rule for parallel resistors is current gets to a point, and then it can choose one path or the other, and then they come back together before they get to any other elements. Okay, so in this case, if current is trying to get from here to here, it can take this resistor or it can take this resistor, and those are the only choices. Okay, so those are parallel resistors. And so R equivalent is equal to 100 times 1,000 divided by 1,100. And that comes out to be 90.91 ohms. And so now we can rethink of this circuit this way. It just goes from the plus 5 through a 90.91 ohm resistor. And then Ohm's law says 5 volts is equal to 90.91 times the current. And so the current drawn from the battery yeah, 0.055. So the current drawn from the battery is equal to 0.055 amps or 55 milliamps. So what we did here is part B. And then what about for part A? So now we want to figure out how much current is going through each of these two branches. They have the same voltage, so each one of these resistors has 5 volts across it. And so for the 100 ohm resistor, we have 5 is equal to 100 I. So I is equal to 0.05 amps. And for the 1,000 ohm resistor, 5 is equal to 1,000 I. So I is equal to 0.005 amps. And notice, just like if you're thinking about fluid flow, the total amount of fluid flow that's coming out of this voltage source has to be the sum of these two pads. You can't make more fluid anywhere, you know what I mean? And so the current going through this branch plus the current going through this branch has to equal the current leaving the battery. Okay, any questions about that? Let me give you one to think about. So let's say we have a battery that's equal to 9 volts. And 2 resistors. Let's make this 330 ohms and 330 ohms. So first, find the current drawn from the battery. And then second, find the voltage with the polarity That's which side is positive and which one is negative. And the current with direction for each resistor. Okay, so first I'm going to figure out the current drawn from the battery. So I'm going to think of lumping these two together. I'm going to think of a circuit like this, where this is just the equivalent resistance. And my R equivalent is equal to 330 times 330 divided by 330 plus 330. And so that is 165. So this resistance is 165 ohms. And now we can use Ohm's law. We know that 9 is equal to 165 I. So I is equal to 0.0545, and those keep repeating. And that's in amps. The directions are the current goes this way and this way. And the polarity of the voltage is like this. And now for part B, we already knew that the voltage for each of these is 9 volts. So we'll go Ohm's law again. The voltage of 9 is equal to 330 I. So the current in one of those branches is 9 divided by 330, which I guess is twice that. 9, half of that. So 0.027 repeating. And so to show it all on a schematic, it would look like this. We have 9 volts for the battery. We have a current going this way of 0.054 repeating. And then we have 9 volts there and 9 volts there. And the current for resistors always goes from the positive to the negative. So the current goes this way for both of them, and it's 0.027 amps for both. So now we have the currents and the voltages with their directions for every one of those elements. So that's everything you would want to know about a circuit. Any questions about that? And if you're ever confused about the direction, really that water flow analogy can help a lot of the time, most of the time. You can tell what direction the water would flow through this loop. Okay, so that's parallel resistors. Let's go back and anybody have any homework questions that you'd like me to go over for the homework that's due today? No? Oh, I thought someone did before. Okay. That's easy. Okay, the next thing that we're going to talk about is using multimeters to measure voltage and current. So far, the closest thing we have to measuring the electrical activity is just hooking up to LEDs. But that's not a very precise way to know what's going on. And so we're going to start using multimeters to measure. So they can measure resistance, voltage, and current. To measure the resistance, like of a resistor, that's pretty easy. You just take the resistor, hook it up to the two terminals, and it'll tell you what the resistance is. The key thing to remember, so it is possible to blow fuses on these. It's not a big problem. They're easy to replace, but if we can avoid it, it's better. So here's the key thing to remember. When using multimeters. First, to measure the voltage, remember that voltage is a difference in electric potential between 2 points on a circuit. Okay, so you always have to have one of your electronic leads on one point of the circuit, another one on another one, and it'll tell you what the voltage is between those two. Okay. To measure the voltage, you just build the circuit as if you weren't going to use the multimeter. And then once the circuit is already flowing, place the multimeter leads to measure. Okay, so when you're measuring the voltage, the multimeter is just like an observer. Okay, if you do that when you're measuring current, it's going to blow the fuse. Okay, so to measure the current, you have to do it differently. So if you do that, to measure the current, it will blow a fuse. So instead, so build your circuit. And then make a break in your circuit where you want to measure the current. So make a break in the circuit where you want to measure the current. and insert the multimeter in that break. You could say insert the multimeter to close that break. So the difference is the voltage, when you're measuring the voltage, the multimeter isn't part of the circuit. It's just observing from the outside. When you're measuring the current, the multimeter has to be part of the circuit. And every time you do this wrong and blow those fuses, it costs our department like 0.4 cents. but Jamie has to unscrew it and replace them. So that's really the. And anyways, might as well learn the right way, I guess. So okay. So to measure the resistance. So now what we're going to do is the resistors, all resistors, they say that they have the colored bands on them that say 330 ohms or 1,000 ohms or whatever, but it's never exactly that. It's always that within some amount of error. And so we're going to take one of these resistors and measure what it is for ourselves. And you're going to so the COM on the bottom of the multimeter stands for the common ground. So that's always going to be your negative. So take one side of the resistor and connect it to the common. And the other side connect to the thing that says voltage and resistance. There's a volts and a ohms symbol. And then once you have that in position, you want to switch the dial to the, I didn't get one myself, but you want to put it to the setting, the smallest setting that's bigger than the resistance you expect. So on mine, so this resistance is 330. So we can't use the 200. We expect the resistance to be bigger than 200. So the next smallest choice is 2000. And so that's the one we're going to use. So once you have it all set up, flip that over to 2000, take your measurement, and then turn the multimeter back to off. Okay. And so so once you have it set up, turn the dial over here to 2K. And mine read 0.323 kiloohms, which is equal to 323 ohms. So I mentioned the silver and gold bands that are on these after the color code. That tells you how exact the resistance is. So if you have one with a gold band, it'll be closer to 330. If you have one with a silver band, it'll be a little, it can be a little farther from 330. Usually that differences like that don't matter much for us, because we're just trying to get currents and voltages into kind of like a reasonable range so that they can power devices. Okay. So now let's measure voltage. So let's do a simple circuit like this where we have 1,000 ohm resistor, and then we have a 9-volt battery. But this 9-volt, that's not it's not going to be exactly 9 volts. It's going to be somewhere around the 9-volt range. So first get out that 1,000 ohm resistor, measure the resistance of that resistor. And then we'll set it up like this. So create that circuit. So it's like so before you use the multimeter, just make this circuit so it'll something like this. So the way it's set up is your common is always expecting to be the negative side of your voltage, and the V lead is always expecting to be the positive of your voltage. So if it has the opposite of that, it just says negative, which just tells you that your volt, usually that doesn't matter to us, but you can still use that number. But that's what the negative is telling you. You just have your lead switched so that your higher electric potential is going into the common instead of your lower. All right, so then for this one, we're going to take, I just pressed my lead to the legs of that resistor, but we're going to go to the multimeter, the common. So this one goes to the voltage and resistance. This one goes to the common. And we want to point to 20 volts here, because again, we want the smallest setting that's bigger than our expected voltage. Any questions about that? Anybody need any help getting this stuff to work, measuring the voltage? Okay, so now this is the dangerous one. Okay, so to measure the current. So first of all, if you look at the meter, notice that there are, so the current on mine is in the lower left. I think that's what all of you have. And notice that there are two settings on at least one of those. There's one with a little m, and then there's one with just a big A. And that's because if you're doing electrical power type stuff, you can have big currents in the range up to 20 amps. And if you're doing electronic stuff, you have very small currents, like down below milliamp or whatever, or at least at milliamp. And so they give you two options for that. And notice that you plug the leads into two different things, depending on whether you want to measure big currents or little currents. Okay, so you're still going to have one that's in the common ground, but the other one is either going to go into the 10 amp one if you're measuring big currents, or the milliamps one if you're, most of the stuff we do is just going to be milliamp kind of ranges. Okay, so let's keep the circuit the way it is. But now we want to measure the current going through that resistor. Okay, so this time what I'm going to do is, so we have this current, this circuit that's already set up. I'm going to make a break in the circuit so no electricity can flow. And I'm going to put my positive lead, my milliamp lead, on one end of where I broke the circuit, and then my common lead on the other side of where I broke the circuit. So it'll look something like this. Okay, so I have my 9-volt battery. And I have my power rails. I have my positive going over to here. And my negative going there. And then I'm going to go from the positive over to one of these and then connect my resistor. But now, so before I made a break in this circuit, I just went from the negative terminal of the resistor back to the negative rail, and then electricity flows. But now I'm going to make a break here, and I'm going to go, instead of having this go back to the negative rail, I'm going to have this go back to the negative rail. And now I'm going to place my leads here. So this one goes to my milliamp lead. And this one goes to my common lead. We expect the current here to be about 9 milliamps. So I'm going to use the 20 milliamp setting. And if you do that, it should give you some value that's, close to 9 milliamps.